Right, hello and welcome to the next talk. It's about in-memory apps with EclipseStore. So my name is Florian. I'm with MicroStream, the company behind the EclipseStore project. And in this talk, I will show you a little overview again about the ideas behind the project and the rationale behind it. And the talk afterwards will be more technical, so we go a bit deeper into object model design, how to code all again. And in this talk, we will talk about the ideas, how you get it installed and configured, and the lifecycle handling. We'll take a look at the lazy loading and how you can store data. We'll check out a bit customization, for example, how to design custom type handlers when you want to customize the way the data is converted into bytes and back. What happens if your classes change? So you have to handle adding fields or renaming fields and so on. And in the end, we check a bit a backup and what about the housekeeping. And if you're coming from MicroStream or you already have a MicroStream project, how to migrate to EclipseStore. So EclipseStore is the successor project of MicroStream. MicroStream itself moved over to the Eclipse Foundation and was split into Eclipse Serializer and EclipseStore. And it's basically the same code base, except it's living in a different namespace, of course, and has different package names. And the migration is pretty easy. We have a tool for that. And so you can continue with the project on EclipseStore. The active development is going to move over to the Eclipse Foundation now, and the MicroStream repositories will be kept open, but only in archive mode. And if you want to get all the new features, I advise you to move over to EclipseStore as a next step. Okay, the rationale, the idea behind it. Current state of the application development with persistence has a single major drawback. You need two data models. As you can see, your application, let's say, lives on a JVM. You have a Java application or different JVM language. You have your Java object graph with it's a graph model. But your data store has a different model, and it's always incompatible, no matter what type of database you use. You got tables, you got key value document stores, and so on. Whatever data store you use, you have to do a conversion. So you need to adapt your Java classes. It's strongly limited, flat Java object model as a result, and to use a highly complex mapping framework. So this object relational mapping most of the time leads to tremendous loss of performance, actually. And in most cases, you need an additional caching framework on top of that, and that leads to a highly complex architecture overall. And to access your data, of course, you need to use a query language or a query API, and that's an infamous source of error as well. And you need most of the time experienced JPA or database specialists. It's a high effort and cost for the entire database development process and maintenance just to store data. And that's where the idea of MicroStream or EclipseStore was born. So it replaces the stack and removes the data conversion altogether. It's a unique new storage approach that stores the Java object graphs natively, which means similar as they are managed by the JVM in the RAM. And That's without expensive transformation, of course, and any incompatible data structure. You only have one data structure left, your object model. And that's the key difference to all database systems and provides you fantastic benefits. And it's a different way to develop because the Eclipse storage library runs inside your application. It's not an external service or an external application you call over the wire, but it's running inside your application. The source of truth now is your application, and the binary data, which can be written to basically anything which takes bytes, your local disk, cloud blob stores, or streaming services, is just like a backup of your data. And the data will be loaded on demand into your Java application and can be used from there. And that's where your data lives now. So it feels like a native Java function for storing data. Like I said, it's only one structure left, the object graph, and there's no more impedance mismatch, no more mapping. And so for that, it's no loss of performance through mapping anymore. And it makes a pure Java in-memory computing paradigm possible, finally. And therefore, you can max out the ultra-fast in-memory computing power of the JVM. So you got the jig compiler, which warms up over the application's lifecycle and has a tremendous impact on the application's performance. And you can even use a pre-compiler for that or native compilation to speed it up even more. And the JVM evolves. So we get the virtual threads now. We have the new garbage collectors and so on, and your application will benefit heavily from the new JVM versions. So you get this as a present for your development. Yeah. And after all, it's of course a more simple architecture. It's easy to use, and it simplifies and accelerates your entire development process and time to market. And like I said, it's a new paradigm. Source of truth now is your application, and the application is in full control of everything, not dependent on an external storage service anymore. Of course, EclipseStore is just a persistence framework. You can combine it with the application framework of your choice. You can use whatever you like, Micronaut, Spring Boot, or Jakarta under the hood, or base your application on different frameworks you already know, and just add EclipseStore as a persistence layer, and you're good to go. So it's an open source project, of course, available at Maven Central, and these are the coordinates. Just use a build management tool of your choice, and you can start your development. EclipseStore was just released as the first final version 1.0, and the next version is in the pipeline already, the 1.1. It's a simple call for a factory method. Just say embedded storage start, and your storage manager is up and running with the default configuration, and the shutdown completes the lifecycle. This is the most simple example, and it will create a new storage if no existing storage is found, and otherwise the existing data will be loaded and can be accessed through the root object. So a bit more configuration. Of course, you want to specify where your data should be stored, in that case on a local storage, just with Java NIO and the path API. You can specify a data directory, or you can use different file system adaptations as well, like S3 in the cloud, or different file storages, and the root object. The root object itself is the entry point of the persistent object graph. Every object which is reachable from this root can and will be persisted and can be restored at any point in time. And at the start of the storage manager, if there's existing data in the storage layer, in a binary layer, the root object will be reconstructed automatically. That's a default behavior. Everything which is not declared as lazy will be loaded eagerly. And I'll show you later how you can define lazy loading points to not load the entire database into the RAM at the startup. So to achieve a more detailed customization, we have various methods. The most low-level one would be the embedded storage foundations. It's a factory type and holds and creates on demand all the parts that form the embedded storage manager. It's a builder pattern style configuration where all aspects of the storage engine can be customized. The library is strictly interface based, so every single aspect of the engine can be customized and exchanged with the embedded storage foundation. So you can inject a new channel count provider with a channel counter 4, you use a different backup directory and so on. And this seems like a bit of an overkill to just set to properties, and therefore we have a more higher level configuration, which lives in this artifact. And it's property based. So you just have a configuration builder, set your properties, channel count 4, backup directory, and from the configuration on you can create your foundation and finally your storage manager, and you're good to go. This configuration also supports external files like XML, JSON, YAML, whatever you're using, and you can load the configuration from there. If you're running on a different application framework like Spring Boot or Micronaut, we have integrations for these frameworks, and you can use the configuration of the underlying framework, and EclipseStore will read the properties from this configuration, so you don't have to use a second configuration just for the persistence layer, but can combine the frameworks effectively. Yeah. Yeah, for example, XML file with the configuration, and then you just call a simple load method, which will create the configuration out of it. By default, we are supporting XML, ini style properties, YAML, and JSON. Of course, it's good for profiles like development, test, and production. And this is all based on a general purpose configuration which integrates in different frameworks, like I said, like Micronaut or Spring Boot and so on. Okay, what about loading data? Of course, you're used to query your database. If you're working with a relational database, let's say you have to fire up SQL statements or use a framework of your choice and load the data, and this data then is most of the time converted into entities or POJOs, and then it can be used. And with EclipseStore, it is different and way more simple. So we have two ways to load data. The first and default case is eager loading, meaning everything which is not explicitly declared as lazy will be loaded. And the subtrees which are loaded lazily can be restored or unloaded at any point in time. And so you can avoid out-of-memory errors. And this is done at the startup of the storage manager. So the root method, or with the root method, you can access this root instance. And in most cases, of course, you check if there's no root present, you create a default one. You're starting
root.update defaults
dataset, and After that, you can access the root with the call to root, and that's all about you need to know about the default loading behavior. So there is no SQL anymore, no query language. It's all done in the background by the engine. Okay, let's say we have a application which contains business years in a map. The business app is our root object. The key of the map would be the year as a number for a faster lookup, and the business year, which contains the turnovers, is in the values of the map. And this approach could be a problem. During the initialization, the root instance would be loaded. From there is a hash map with all business years, and each with its own list and all turnovers. So for all years, let's say we have 20 years with 1 million sales, makes 20 million entities, which are pumped directly into the RAM at the start. And it doesn't matter if someone needs it or not. We don't want it that way. We just didn't partition our model just to load everything anyway. And it, of course, would be nice if you could just simply add a lazy to the turnover list, which we want to load lazily. And that's exactly how it works. Just wrap it around your subgraph, which you would load lazily. And that's all you have to do. So how can we access the content of the lazy reference? It's just a simple getter. And the engine checks if the subgraph is loaded. Otherwise, it will load the data, create the objects, and therefore, from there, you're good to go. And of course, you don't have to fire up select Stern for select all from turnovers where ID is whatever. It's all done in the background by the engine. The engine itself has a technique called Swissling. It automatically assigns unique IDs to all Java objects or to all instances living in your application. And therefore it knows where the data is stored, what it has to load, and it's fully managed in the background. So you don't have to worry about technical IDs anymore. So there's no need for auto increment keys you have to put into your POJOs or foreign keys and so on. It's all done by the engine in the background. Of course, if you have IDs like customer IDs, which you need for invoicing, or ISBNs in books and so on, which are part of the business model and not low-level technical IDs, you put in this IDs into your objects, of course. So I'm talking about technically low-level IDs. These are not needed anymore. So one thing we get asked all the time is, why did we choose a type for lazy and didn't just use a annotation for that? If we would use an annotation, we wouldn't have a control mechanism accessing the underlying object, in this case, a list. So we would have to work with bytecode manipulation at runtime. And that's what we didn't want to do. So that's the first point. And the second one is annotations can only live in certain places. And for this example, if you want to lazy load only the values of a map, it wouldn't be possible because you cannot write lazy inside of or annotations inside of generics. So that wouldn't be possible if you used an annotation. That's why we decided to use the lazy as a concrete type, and you can use it in your object model. There are several ways to initialize lazies. Of course, the lazy dot reference creates a new lazy with an existing value. It can be used as a null value or null at all. And if you access it, of course, you do have a null check. Let's say we have a lazy list in our object, and we want to return the turnibers. We have to check if the lazy itself is null. Otherwise, we can call the get. But we got a convenience method for this. Just say a static lazy.get, and the null check is done inside this getter method, and it will return the list of turnibers if there is any data. And here you can see the lazy, of course, is part of your implementation detail. So the object, the business year itself contains a lazy list, but the external user of the business year just calls a get turnovers and doesn't have to worry about lazy loading. It's hidden inside the domain model, inside the domain object. And I think that's the best design to not expose a technical detail like lazy loading to the outside. All right. So as a complete example, let's see, we have a lazy turnover list. The getter is wrapped in the lazy. And if a new list is coming in, we just create a new lazy reference and add it to our, and assign it to our turnovers. And this is all you need to know about lazy loading. There are some more usable methods, of course. The lazy get will, like I showed you, load the data on demand. The lazy peek will just look up the existing state. If there is null will be returned and nothing will be loaded. So you can check the state of the lazy reference. And of course, there's a lazy clear, which removes the data out of the removes the data from the heap, and the garbage collector can clean it up. And with the clear method, you can control what data lives in your memory, and but that's a kind of hard to do if your application gets bigger, and therefore we have an automatic lazy reference manager which does this job for you. It is configured with a checker which works with a timeout or a memory quota, and the lazy reference itself tracks the time of their last access, the creation point and the last query point. And if an instance is deemed to timeout because of the timeout of the checker, it will be cleared. So the hot data, which is used all the time, will automatically stay inside your RAM, and the cold data, all the older business years, for example, will be cleaned up by the lazy reference manager eventually if they are not used for a while. So with this technique, the hot data automatically stays in memory, and most of the time, of course, you don't have to worry about clearing the lazy reference. The lazy reference manager will do that for you. Yeah, that's all you need to know about loading data. Everything's eager, except it's declared as lazy, and the lazy getter will do the job for you, and the clearer will remove it again. And that's all you need to know about loading data. Storing is quite simple as well. Just store the modified object. Tell the engine which objects have changed and call a simple store method on that. And a store method is an atomic all or nothing operation, meaning if the store call is successful, all data is written to the storage, otherwise no data is persisted, and partially persisted data will be reverted. But that only will happen if an IO error occurs, so in a very ill scenario. So store the object which was changed. If you update the root, we have a special store read method for that. If you change a field of, let's say, a customer, just store the customer. And if you add an item, you basically do an insert. You have to change. You have to store the collection, because what you have changed is the collection itself. You added an item to it, so therefore you have to change to store the list, and that's about it. Of course, if you want to span a transaction around, or you want to store multiple objects at once, we have a store all method for that. Hand over various objects and they will be stored inside a single atomic operation. And that's how you can span a internal transaction around multiple stores. The store or store all methods, what happens in the background? A store is created. Every changed object will be registered at the store with a store command, and the commit is called in the end. And that's what happens if you call a store method of the embedded storage manager or a store all method. So the default store which is used is a lazy store. Lazy store stores everything which is new and which or every object you hand over directly and every new object from there. So if you store an existing customer and the customer has a new purchase in it, the new purchase will be stored as well because it's new to the storage engine. And if you're not sure what's changed, you can use an EclipseStore. The EclipseStore stores everything from the given object on. So everything which is reachable from the handed over object will be stored safely. So if you're not 100% sure what has changed, you can use the EclipseStore. Of course, it comes with a performance cost because you have a bigger transaction, a bigger throughput is needed. But most of the time, of course, you know what objects are changed. It's your software after all, so the lazy store should be enough. So you can configure the eagle storing in different ways. Either you call the eagle storing by hand, like this code sample, or you can say every time something is stored lazily, I want to force eagle storing on fields in my type. Let's say we have a class where a list of items lives, and every time we want to, and the owner class or the owner object gets stored lazily, we want to force an eagle store on the item class inside these objects. It can be done with the field evaluator. It's just a simple predicate. Let's say we define an annotation called eager, put an eager annotation over the items. We just say if this field has this annotation present, it returns true, and this field will be stored eagerly all the time. Or you can use a name prefix check or whatever you like. And so you can control the automatic eager storing behavior of the engine. So either you customize it or you call it manually. And that's the two ways to use eager storing. What about transient fields? Meaning we want to exclude data from the persistent layer, meaning you have computed fields, temporary flags, stuff like that, or basically stuff in your POJOs which shouldn't be persisted or restored after they are loaded. The default way is to put the transient modifier in the field definition, and that can be customized as well. We use transient because most of other serializing or persistence framework do this as well, but you can configure it. It's another field evaluator where you can say, for example, every field which starts with an underline should be transient, or should be stored. In this case, all fields which return where the field evaluator returns true should be stored, or every field which contains an underline should not be stored. And so you can work with prefixing or whatever you want to use for that, or annotations again. Yeah. So about deletion. Okay, deleting data again does not require an explicit deleting actions like a delete from table where condition is met. Instead, you just clear any references to the object in your object graph and store these changes. It's like it's done in Java. If there are no more references to a certain object, the garbage collector will clean it up eventually, and the object is gone. And that's the same with in the storage layer as well, because EclipseStore just stores the state of the object graph and behaves in the same way. So you remove an item from a list, and if it was the last reference for this item, the garbage collector, which we have on a storage layer, will clean up this data eventually. And the deleted data, of course, is not erased immediately from the storage files. It's done by the housekeeping process, which runs in the background. But if there is no reference to the object anymore, you won't be able to access it anymore anyway. But just the binary debris will be swept out by the garbage collector in the background. So that's all about CRUD. You need to know. We've seen how the data will be loaded lazily and legally, storing as well, and deletion is just removing references and storing that changed object, and the rest is done or managed by the engine. So very simple CRUD stuff. So we have time left to go into a bit of customization. For example, custom type handlers. EclipseStore is based on the Eclipse serializer, and the serializer can be customized how to create the binary representation of an object and the basically how the serialization on a byte layer is done. And with custom type handlers, of course, you can optimize the performance and memory consumption for complex objects or objects which are used heavily in your application, and it can be done with external configuration for arbitrary types. Let's say you use a third-party library and want to customize the serialization for external types. You can do it because we use custom type handlers, external type handlers. You don't have to own the source of the types you want to customize. EclipseStore itself brings specialized and optimized type handlers for the most commonly used types anyway. For example, the collections in a JDK or date types and so on. So types which are used most of the time in business applications have special type handlers, optimized type handlers. And for every other object the engine encounters, a generic type handler will be generated. And for this time slot, for example, the type handler will function, or every type handler functions that all the primitive data is embedded in a record and all objects are created as new records and linked with an object ID to keep the referential integrity. So we have a time slot class, for example, out of censoring data, which comes in thousands or 10,000s a minute. So we really want to optimize the binary state for this type because we want to save RAM and storage. So we can do it. The default generic type handler will analyze the type in the following way. We have an object ID. It's the unique ID for this instance. We have a type ID, Then comes the primitive data, in that case, the slot number. And then there are two datetime objects, which are new records, and they are referenced in the time slot by their object ID. And the data in the datetime is just the internal timestamp. So it's a lot of overhead just for a slot number and to timestamp. So we want to optimize it and embed the timestamp in the time slot record directly. And so we effectively shrink it down about 60 or 70%. And that's a lot of gain for a simple type handler, which can be created in two ways. Either you can, if you own the source of the type you want to customize, you can just put a static method which returns a type handler, and the engine will use that one, or you can define an external type handler and register it in the foundation. We have a builder style API for type handlers. For the most cases, it should be enough. You define a type handler, define what type should be handled, and then the fields. Each field handler just says, I convert part of the object to a primitive value, and I restore the primitive value. And that's all the type handler has to do. Just create primitive values and restore the primitive values. And then you have an optimized binary output for a certain type. A different way to do it would be a custom type handler. For, let's say, a type in a JDK, a buffered image, which contains image data of some sort, but we want to enforce that the binary representation should be PNG encoded. So we just convert this buffered image to a PNG with the image.io API and store this bytes into the transport, the binary type, which the binary type is the medium object which transports the bytes in and out, and just register which bytes should be written and read from it. And then you register this custom type handler before you start the engine, and then you can use the type handler for third-party types as well. So what about type mapping? Let's say you change your objects, and you will do that over the lifecycle of your application. And there's always a version 2, 3, and so on. It can be done. We have a technique called legacy type mapping in the framework, and it does the changes from version to version. So you can have multiple versions of single classes, and the type handler, the type mapper, will convert older data from version through version until it is at the version of the actual class in your class path. For the most common cases, for simpler cases, it's done automatically, like just a rename is discovered easily, or if you have a primitive type conversion from int to long or a float to double, the engine will do it automatically. But if you have more complex cases, like say you split name into first and last name, you can provide a custom type mapping for that. So you can configure how the data should be converted, or converted from version to version. And so you can control how the data flow lives throughout your application. The data conversion from an older version to a newer version is only done on demand if an object is loaded into memory. It's not the whole storage will be rewritten if the engine encounters new types, but only on demand. And there's basically no performance overhead, because most of the times the bytes are just written to a different location in the RAM, and therefore the type mapping goes in the flow of the loading process. Yeah, the type mapping can be provided either by simple text files. You say what's the old stuff and what's the new stuff. Either you rename classes from old to new contact, or you rename fields, or you delete fields in this case. Then there is no old stuff, of course. There's no new stuff. In this case is an addition of a field. Or you can do it by code. There's an API for that as well. So we have a bit more time, of course. We say you can configure two backups, continuous and a full one. Continuous backup writes to a different storage target. You can use different file systems. Let's say a live data lives on a local disk and the backup lives in a bucket in S3. You can do that, of course, or you can issue full backups to create full backups with cron jobs, for example, overnight. And the housekeeping process, which takes care about the old data removal in the storage, and the garbage collection, which removes the unreachable objects in the storage, can be configured with the configuration of the interval and time budget, and the default should be fine for most use cases, but if you have a really write-heavy operation and the housekeeping has to do more work, be advised to give the housekeeping more time. You have to do it manually right now, but there's a feature coming up, the adaptive housekeeping, which will increase the time for the storage for the garbage collector in the background, so you don't have to worry about the slow level stuff anymore. And all the jobs the housekeeping does can be called manually again in cron jobs, just to clear out the storage if you have write-heavy operations. So before we can answer the questions, of course, the migration, how do I migrate from MicroStream to EclipseStore? We have a command line tool for that. Just go to the storage migrator module in our repo. There's a description what command lines you have to call to migrate either your code base or your storage itself, or the storage. And these are one or two simple command lines, and you convert your code base and your storage from MicroStream to EclipseStore, and you can use the new features for that. All right, so let me have a look in the chat. All right, so if the data changes several times, I need to keep all versions of the changed classes. You cannot do that. So the class can only live once in your class path. And therefore you have to keep the mapping from version to version, but the class itself is always only on the newest version in the class path, because you can't have two versions of a customer, let's say, in your class loader. So custom type handlers seems like something that one would want to use for most classes. Writing handlers seems rather involved. Could annotations be used instead? Yeah, what we offer right now is the builder pattern style and various abstract supertypes for use cases, for single value, for multi-value stuff, for list stuff. You can write, it's just a few lines of code to customize it. We are always open for new ideas to get this done more easy, or with shorter, concise code. Of course, it's a lot of the stuff you have to do to convert stuff to bytes and back, and so the more easy the code is to customize it, the more safe it should be to avoid errors, of course. Quarkus integration, yeah. We do have, MicroStream has a Quarkus integration. That's the Quarkus integration is part of the release 1.1 of EclipseStore. There are some modules we couldn't bring over to the Eclipse Foundation for legal reasons yet, but they will be moved in the next release. Like the cache Quarkus integration is part of it. Yeah, and Spring Boot is a part of this as well. Yeah. So, all right, I don't see any unanswered questions. Feel free to use your mic as well, or just put it in a chat. We have a few minutes left. On the other hand, we in my next talk in 10 minutes, we can do a deep dive on your questions as well. So we got plenty of time for that. Right. Yeah, some questions how when multiple processes or multiple users will access the same object graph. I will go into that in the next talk, because that's the drawback when you have one shared object graph. You have to handle the concurrency stuff, and yeah, I will show you this in the next hour. All right. So then see you in 10 minutes. And like I said, we will have plenty of time to answer more questions there, or there's another talk in the afternoon where we show what's cooking, on what we are currently working, and we have a lot of time for Q&A there as well. So thanks for now, and see you in a few.